Welcome to my talk. I'm Alejandro Tolcachier from Universidad Nacional de Córdoba, Argentina. Thanks to the organizers of this session for the opportunity to give this short talk. I will try to explain an elementary classification I obtained about six-dimensional almost abelian flat solvmanifolds using tools related with the problem of classifying conjugacy classes of integer matrices with finite order. This talk is based in an article submitted on arXiv with the same name. First, I'm going to introduce the objects we want to classify. Given a solvable Lie group G, we will say that gamma is a lattice if it is a discrete subgroup such that the quotient is compact. And we will call solvmanifold to a compact manifold obtained as a quotient of a simply connected solvable Lie group by a lattice. It is well known that every simply connected solvable Lie group is diffeomorphic to Rn. This implies that solvmanifolds are aspherical, that is, higher homotopy groups are trivial, and also implies that the fundamental group of a solvmanifold is the lattice gamma. Moreover, Mostow proved that solvmanifolds with isomorphic fundamental groups are diffeomorphic. In particular, they are homeomorphic if and only if they are diffeomorphic. In general, it is difficult to construct solvmanifolds because it is difficult to know whether a given solvable Lie group admits lattices or not. In the nilpotent case, there is a criterion due to Malchev, and in the solvable case, it is only known a necessary condition that the group must be unimodular, which in the connected case, it is equivalent to say that the trace of odd operators in the Lie algebra must be zero. We want to study solvmanifolds endowed with a flat Riemannian metric induced by a flat left invariant metric on the Lie group G. It is known that every compact flat manifold is isometric to an orbit space of Rn by a subgroup of isometries, which acts properly discontinuously. And it is not difficult to see that this is equivalent to gamma being discrete and torsion-free. Such a group is called Bieberbach group. These groups were studied by Bieberbach. The most important theorem to us is that every Bieberbach group has a free abelian normal subgroup lambda of finite index, which is maximal as a normal abelian subgroup, in the sense that contains every other normal abelian subgroup. We can identify the Riemannian holonomy group of the compact flat manifold with the quotient of gamma over lambda, which is a finite group by Bieberbach theorem. This implies that the holonomy group of a flat solvmanifold is finite, and furthermore, it is abelian. We give an elemental proof of this fact in an article published in 2020. The other two Bieberbach theorems in the context of flat manifolds say that two flat manifolds with isomorphic fundamental groups are affinely equivalent. That is, there exists a diffeomorphism which preserves the Levi-Civita connection. And furthermore, there are a finite number of affinely equivalent classes of compact flat manifolds in each dimension. Here I put a table with the number of Bieberbach groups in low dimensions. To obtain flat solvmanifolds, we have this criterion by Milnor of when a Lie group admits a flat left invariant metric. And this happens if and only if the Lie algebra splits as an orthogonal sum of an abelian subalgebra and an abelian ideal, where the action of B in U is by skew-symmetric endomorphisms. Barberis Dotifino decomposed even further the Lie algebra as B plus the center plus the commutator, and it holds that the adjoint representation restricted to B is injective, the commutator is abelian and even dimensional, and the dimension of B is less than or equal to half the dimension of the commutator. We will say that G in the conditions above is a flat Lie algebra and G a flat Lie group. Note that a flat Lie group is two-step solvable because the commutator is abelian and unimodular because the odd operators are skew-symmetric. We want to study flat solvmanifolds obtained as quotients of almost abelian Lie groups. In general, A Lie algebra is said to be almost abelian if it has a codimension 1 abelian ideal. That is, we can write G as a semi-direct product of the span of some x and the abelian ideal, and the action is the adjoint representation. The corresponding simply connected Lie group is a similar semi-direct product where the action is the exponential of t multiplied by add x. The advantage of almost abelian Lie groups is that there is a criterion due to Bock to determine when the Lie group admits a lattice and to determine all its lattices. The condition is that there must be a T0 non-zero such that phi of T0 is similar to an integer matrix. In this situation, the lattice looks like this, where P is the matrix which conjugates. Note that there might be several integer matrices to which we can conjugate phi of T0. And we can write this lattice gamma in a nicer way because it is isomorphic to the semi-direct product set by set M, which we will denote sigma E, where E is the corresponding integer matrix and the multiplication in the group is given by this formula. In the previous article, we gave an elementary classification of flat solvmanifolds in dimensions 3, 4, and 5, which all are obtained from almost abelian Lie groups, so we were able to determine all its lattices. In dimension 6, we have two possibilities for the dimension of B. If it is 1, then the Lie algebra is almost abelian, and if it is not equal to 1, then the Lie algebra is non-almost abelian. In the article on which this talk is based, we also obtained the classification for certain lattices in the non-almost abelian case. But here I wanted to talk about the almost abelian case because it is very rich on its own. So, let G be a 6-dimensional almost abelian flat Lie algebra. Then, since AddX is skew-symmetric, then there must be a basis where AddX looks like this, where A will be 0 or not depending on the dimension of commutator, but B is non-zero. And thus, phi is the exponential, and we get this matrix of sines and cosines and this one above. We will write phi as the direct sum of these matrices, where theta is this matrix of rotation, and note that the determinant of phi of t is 1 for all t. We want to classify all the 6-dimensional almost abelian flat solvmanifolds. To do that, we have to use Bock's criterion and find T0 such that phi of T0 is similar to an integer matrix. Once we find the T0s, we must determine to which integer matrices we can conjugate phi, up to conjugation in GL5. The reason of this is that if A is similar to E or its inverse in GLZ, then the lattices are isomorphic. A curious fact is that the converse of this seems to be false. See this question in Math Overflow. And then, once we obtain the integer matrices, we have to classify up to isomorphism the corresponding lattices sigma E. First, if we want phi of T0 to be similar to an integer matrix to get lattices, it must have finite order. Considering this condition, the values of T0 are the following, which in fact depend on AT0 and BT0. And it is easy to see that interchanging AT0 with BT0, adding 2 pi or choosing 2 pi minus AT0 will give rise to isomorphic lattices, so we can work only with the values in red. One comment about the proof: the sufficient condition is straightforward, and the necessity is because the characteristic polynomial of phi of T0 must be integer, and since phi has finite order, P is a product of cyclotomic polynomials. So we can determine all the possible P's and then look at the eigenvalues. And this method works in any dimension. Now we want to determine for each T0 the integer conjugacy classes of integer matrices to which we can conjugate phi of T0. We deal first with the case of matrices of order 2. In our case, we get these two matrices. An old lemma states that if A squared is the identity, then it is integrally similar to a matrix W of this form, where X, Y, and Z satisfy this relation. For n equal to 5, we obtain the following set of representatives for the integer conjugacy classes of matrices of order 2 in SL5. And by looking at the Jordan form, then we can see that the second phi we obtain is similar to the first two matrices, and the second one is similar to the last three. In what follows, by looking at the Jordan form of phi of T0, it will be similar to the corresponding integer matrices, so I will not repeat it. For the case when the order is not equal to 2, we will determine explicitly the conjugacy classes in SL5 of certain integer matrices, using tools developed in a paper by Yang, where the case n equal to 4 is treated. Everything is based in this lemma, which says that every integer matrix is integrally similar to a block triangular matrix, where the matrices in the diagonal have irreducible characteristic polynomial. And moreover, this triangularization can be obtained with the diagonal blocks in any prescribed order. Some notation: given a monic integer polynomial P of degree n with independent term equal to plus or minus 1, we denote by calligraphic M sub P to the set of conjugacy classes of invertible matrices n times n with characteristic equal to P. This set is non-empty because it always contains the companion matrix of P, Cp. And C sub n will denote the companion matrix of the nth cyclotomic polynomial. Later, we will use that for the cyclotomics, the cardinal of this set is 1 for n less than 23. That is, there is only one conjugacy class. More notation: given an invertible matrix A, we denote by A plus and A minus to this matrix, where we added a column with the canonical vector 1 and a row with plus or minus 1 at the end. And also we denote by calligraphic M sub A to the set of n times n integer matrices with characteristic and minimal polynomials equal to those of A. We are going to use the following theorem of Yang. For n greater than or equal to 2, let A be a direct sum of S blocks of the matrix Cn. M be the matrix A with an M identity below, and X of the appropriate size. If n is a power of a prime, then M is integrally similar to a direct sum of T blocks of Cn plus S minus T blocks Cn plus an M minus T identity, where T is between 0 and the minimum of S and M, and it is uniquely determined by M. If n is not the power of a prime, then A is integrally similar to the direct sum of A plus the identity. With these tools, we can easily solve case 1. Recall that in this case, phi of T0 is the 3 identity plus the rotation matrix valued at one of these 3. The characteristic polynomial is x minus 1 cubed times the corresponding cyclotomic, and the minimal polynomial is x minus 1 times the cyclotomic. A matrix P, similar to phi of t0, must have the same characteristic and minimal polynomials to those of phi of t0. Then, by the previous lemma, B is integrally similar to a block triangular matrix where the characteristic of A11 is the ith cyclotomic. Since the minimal of B is x minus 1 times phi I, then this block below must be the identity, and also, as there is only one conjugacy class of matrices with characteristic polynomial equal to the ith cyclotomic for E equal to 3, 4, 6, we can assume that A11 is equal to Ci, conjugating the block above if necessary. Then B is integrally similar to a matrix of this form. And now we can use the theorem. There is only one block of Ci and the 3 identity, so B is integrally similar to one of the following, depending on I. Note that since 6 is not the power of a prime, there is only one matrix. Case 4 is very similar. We have phi of t0 for these 4 pairs of values. In this case, both the characteristic and the minimal polynomials are equal to x minus 1 times the ith cyclotomic, where I in this case is 5, 8, 10, or 12. By the lemma, a matrix similar to phi of t0 is integrally similar to a matrix which looks like this. And by the theorem, we have the following possibilities. For cases 2 and 3, we introduce the notion of AB equivalence. Given A in GLM and B in GLN, such that their characteristic polynomials are coprime, we define a linear transformation of the set of m times n integer matrices in itself, given by psi of t equals to at minus tb. Choosing an appropriate basis, it can be seen that the determinant of the endomorphism psi is equal to the resultant of the characteristics of A and B, where the resultant is defined as the determinant of the Sylvester matrix given as follows. Put the coefficients of PA in the first row and then repeat them diagonally as many times as the degree of PB, and then do the same for PB. It is known that since the polynomials are coprime, then the resultant is non-zero, and thus psi is injective. The image of psi will be denoted by AB between angles. And quotienting the whole set by this image, we have the cokernel of psi, which has order R equal to the resultant of PA and PB. We define now an equivalence relation that will be very important to our problem. X and Y are said to be AB equivalent if there are matrices P in the centralizer of A and Q in the centralizer of B, such that xq minus py is in the image of psi. The set of AB equivalence classes will be denoted by SAB. From the definition, it follows that if x and y are in the same class of the cokernel of psi, then they are AB equivalent. And an important fact we will use is that if the order of the cokernel R is equal to 1, then there is only one AB equivalence class. And if R is greater than 1, then the cardinal of the set of AB equivalence classes is greater than 1 and less than or equal to R. This concept of AB equivalence allows to solve the problem of determining the integer conjugacy classes of block triangular matrices. Indeed, take A and B integer matrices such that their minimal polynomials are coprime, then these matrices are integrally similar if and only if x and y are AB equivalent. I'm going to give an example of case 3 to show how to use these tools. Take phi of t0 with this pair of values. Here both the characteristic and minimal polynomials are equal to x minus 1 times phi 3 times phi 6, and by triangularization lemma, a matrix P similar to phi of t0 must be integrally similar to a matrix with C6, C3, and a 1 in the diagonal. And we group the block below under the name of D. By the theorem, D can be integrally similar to either one of these two. For this choice of blocks, the resultant is equal to 4. We compute the cokernel of psi. For this D, X is in the image of psi if and only if there is T such that X is equal to C6T minus TD. And it is not difficult to see that these are the conditions for the entries of X. From this, it can be easily seen that these matrices form a set of representatives of the cokernel of psi. Now, from these classes, we have to look for C6D equivalences. And in fact, choosing Q equal to D and P equal to the 2 identity, we obtain that E11 is equivalent to E12. And likewise, E11 is equivalent to E11 plus E12. As R is greater than 1, there are two classes given by the class of 0 and the class of E11. The computations for the other matrix D are similar, and we also obtain two equivalence classes. In conclusion, a matrix P similar to phi of t0 is integrally similar to one of these four. In the same way, cases 2 and 3 can be solved. The last thing we have to do is to classify the lattices corresponding to the integer matrices we obtained. Two invariants we can easily compute are the holonomy group and the abelianization of gamma. Recall that gamma is isomorphic to sigma e, which is certainly nicer to compute the abelianization. Regarding the holonomy, in the previous article we proved that the holonomy group of an almost abelian flat solvmanifold is the cyclic group of order equal to the order of matrix phi of t0. And regarding the abelianization, it is easy to see that the commutator of sigma e is given by 0 plus the image of the identity minus e. From this, the abelianization can be easily computed. For some matrices, we could not distinguish the lattices from the holonomy group or the abelianization, so we had to appeal to other methods. For the cases when the matrices are of order 1, 2, 3, 4, or 6, we have this proposition, which gives us a necessary condition for the lattices to be isomorphic. And this proposition effectively allowed us to distinguish the lattices. These are the tables we obtained. The lattices corresponding to matrices with the same symbol aside cannot be distinguished only from the holonomy or the abelianization. But with the proposition above, we could distinguish them all. And for matrices of order 12, we appeal to computational methods to distinguish the groups. For example, introducing them in magma and computing the size of subgroups of index less than or equal to 10. We thus obtain 48 solvmanifolds. Many thanks for your attention. I look forward to your questions. I leave here the bibliography.